This video contains the solution for problem number 3 from the 2006 AP Physics C Mechanics exam. We have here a thin hoop rolling down a ramp. Angle is theta. Roll off and hit the ground. And we knew this. Hey, hoop is mr squared. Everybody knows that. It told us anyway. It's released from rest at the top of the ramp. A distance L here. And let's see, table is height h above the floor. Assume that the hoop rolls without slipping down the ramp and across the table. Express all algebraic answers in terms of given quantities and fundamental constants. Alright, part A, derive an expression for the acceleration of the center of mass of the hoop, so it's a linear acceleration as it rolls down the ramp. I like to do energy considerations with this kind of problem. So let's take that approach and see how that goes. So let's see. We have, how far is it dropping? Looks like it's going to drop. This would be, that's opposite to that angle, so this would be L sine theta right here. So the mass, we're turning all of its potential energy into all of its kinetic energy down here, and we'll try to find some information about that. So its potential energy would be mgh, so that's capital M, that's the mass there, times g, times L sine theta is the height. That's its potential energy. Now remember, when something's rolling, it's not just 1/2 mv squared. It's also, some of its energy is going to be taken up by the rotational kinetic energy. So we've got to take both those into account. So let's see. Regular old kinetic energy is 1/2 mv squared. Solve for that v later. Plus rotational kinetic energy is 1/2 the analogs of these. That's I, moment of inertia, which is mr squared. He told us that. Times omega, that's angular velocity squared. And remember, that's v over r. So maybe right away I'll say I don't really want to deal with two different kinds of velocity, so I'll substitute v squared over r squared here. Let's do a little simplifying. Let's see. Looks like we have a v here. So if you look back at the problem, we're actually doing part B first. To derive an expression for the speed of the center of mass. So using this energy consideration, you actually end up solving B first, and then we can get A from that. So I'm going to go ahead and mark this part B. Simplifying this, these r squareds cancel out. I have 1/2 mv squared plus 1/2 mv squared, which is mv squared. So mg is L sine theta. The m's cancel out, and we get v is equal to the square root of g L sine theta. And that's the answer to part B. So let's go back to part A and see if we can't figure that out. Derive an expression for the acceleration. Well, its initial velocity was 0. Now we know its final velocity, and we know the distance it traveled. So this is an easy kinematics problem now. See, we know initial velocity is 0. Final velocity is this. We just found in part A. The distance it traveled, or you could write that as x if you want, is L. And we want the acceleration. So that's the vf squared vi squared equation. So we have the square root of g L sine theta squared, that's vf squared, equals vi squared plus 2 times the acceleration we're looking for times L. So let's see, that's g L sine theta equals 2AL. Looks like the L's cancel out, and we get that A is equal to g sine theta over 2. Alrighty, that's A and B done in the reverse order, but you know, this This clearly was going to be fruitful, I think, so even though we ended up doing B first, I think it's okay if you end up doing something like that. Don't turn back. You're going in a good direction. All right, part C. Derive an expression for the horizontal distance from the edge of the table to where the hoop lands on the floor. Oh boy, this is easy stuff. This is like chapter 2 kinematics or something like that. So what's the horizontal distance? Well, we're just going to set up our, let's see, we know its final velocity when it got to the bottom of the ramp was square root of GL sine theta. So let's set up our vertical and horizontal. So let's see, the acceleration of this is negative g. The distance, delta y, is it's dropping a height of h, so that'd be negative h. And its initial velocity in the vertical direction is 0, right? Because it rolls right off the ramp this way. So its initial velocity in the vertical direction is 0. It's been a while since we've done this, but remember how this goes. And I'd like to know the time. So that is our old favorite equation, that displacement is equal to initial velocity times time. Initial velocity is 0, so that's gone. There's 1/2 at squared, so that'd be 1/2 a t squared. So it looks like time is going to be equal to 2h over g, the square root of 2h over g. All right, and that is the same time. And hey, time is time, so when it hits, it hits. So 2h over g, and the horizontal velocity is this, right? So Vx, we're going to call it now, as the square root of GL sine theta. And if you want to know how far something goes, you multiply its velocity by its time, if it's a constant velocity. So its displacement in the x direction is these two quantities multiplied together. Since they're both square roots, I can just combine them. So that's, see on the top, 2h GL sine theta. That's all that stuff. Then a g on the bottom. Those cancel out. So I guess our final cleaned up answer will be 2HL sine theta. That is the horizontal distance that it goes. And last, suppose that the hoop is now replaced by a disk. Well, a hoop, this is like maximum moment of inertia for a rolling object like this. mr squared, all of the mass is around the edge. So a disk will have less, if you don't remember. It's actually 1/2 mr squared. You probably remember that. Having the same mass m and radius r. How will the distance from the edge of the table to where the disk lands on the floor compare with the distance determined in part A? Well, I'll go back to our part A, or part B that we did first. Remember, what's happening here is the energy is being split up between translational energy and rotational energy. And the higher this is, the more energy this is going to take up, right? So a hoop is taking like the maximum. If the moment of inertia had been 1/2 mr squared, this would only have been 1/4, and then we would have got a greater velocity. So the smaller this is, the more of the energy actually can contribute to its translational motion. So that means it's going to go farther. So less of the moment of inertia will be occupied by the rotation. So the distance will be greater than. And we'll justify it something like what we just said. Because the moment of inertia of a disk is less than a hoop, more of the initial potential energy is transferred, I suppose we could say, maybe that's not the best word, but transferred to translational kinetic energy. So the velocity when a disk leaves the table is greater. You can check out their rubric and see what they say, but that would definitely get all the points for that. You get a point for picking the right one, and I think 2 for having a good explanation. Not too bad.